Good evening. It's great to see these many people out here. I'm a geologist. I look at the rocks, one of those crazy guys. And the interesting thing is that the rocks tell the history of the Earth. There's very little about the history of the Earth that you cannot find in the rocks. And this is something that the average individual is not aware of. So when I was asked to do this, I had said, well, I'm going to stick with the rocks. I'm not worried about atmosphere. I'm not worried about the galaxies. I'm going to stick with what the rocks tell us. And what I want you to take away from this is that the Earth climate has gone through a repetitive series of oscillations. And those oscillations go from glaciation, which is the blue stuff on the bottom of the slide, to evaporitization, which is the red stuff at the top of the slide. And consistently through geological time, we have gone back and forth and back and forth in what you can almost call the climatic waltz. My grandfather taught us all how to dance the waltz. And he said, it's not 1, 2, 3, 1, 2, 3, 1, 2, 3. It's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It's cyclic. And that's basically what we see here. And you'll also notice that when the little cursor is dancing up and down, it's actually dancing because there's more, it's not just one order of oscillation that I built into this. There's several orders of oscillation. So there's many different things taking place at the same time on the general curve. So what I'd like you to do is to, if you don't take anything else away from this, is to recognize that in 600 million years, the Earth's climate has oscillated between glaciation and evaporitization, and I'm going to take you through those extremes. And the one thing, we are living in a glacial, interglacial oscillation at this point in time. And so I will talk about where that might take us. The other thing is that remember that all the information we need for the Earth and its climate can be found in the rocks. I was watching Land and Sea the other night, which is a program for the East Coast. And they asked this octogenarian fisherman what he felt about the weather as it was occurring in Newfoundland at this point in time. His real severe weather has been going on. And he said, you know, if you were born less than 50 years ago, you're not old enough to be able to assess the changes in climate. And I kind of got a kick out of that, and so I thought I'd draw attention to it, that if you're going to look at climate change, 1,000 years is not enough. 800,000 years is not enough. In fact, in 20 minutes, 600 million years comes down to about 600,000 years a second. So to give you some idea what we're seeing there. There are a number of buzzwords going around at this point in time. First one I'll draw attention to is recorded history. Well, recorded history to most people means the written word. But recorded history is billions of years in length because it may not be handwriting, but it is a language that we get from the rocks. And so recorded history goes all the way back. So when people tell us that the hottest time in recorded history, well, it may be in a few human years, but from the point of view of the Earth, it's meaningless, it's not true. The other point was our policies will be evidence-based. We've been hearing this from our local environmental minister. I don't even know what they mean by evidence-based, because many people include data with interpretation, which is a scientific error. There's no way that you present interpretation as data. And I'm quite convinced that when they say it's evidence-based, they're really talking about the interpretations that are being provided to them and not the actual data. We're going to talk about some data. Climate change. I haven't found many people even know what they're talking about when you ask for a definition. And because the definition of climate change for the last 1,000 years is a different definition than the one for 600 million years. So, you know, it's all relative. Who are you speaking with, and what do they mean? Then global warming is just one part of the curve. It could be warming, but then it cools. And so the global warming is just a very, very short-term factor at this point in time. The real story is in the rocks and in geologic time. It's a four-dimensional system. Just talk about some climate points. The sun provides us the heat and provides us with the light for us to exist. That is a critical element. However, the Earth is a dynamic system in itself. So it superimposes a lot of very basic aspects into climate change. The climate change is real. There's no doubt about it. It's been going on for billions of years. It's going on now, and it'll continue for as long as the Earth continues. Climate history can be seen in the rocks. And when we talk about glaciation, we're talking about temperatures that can get to be less than 80 degrees centigrade. 2 weeks ago, it was minus 44 in the Arctic, on the Arctic Ocean. So when we look at temperate zones, we're looking at lots of vegetation. We're looking at rocks without calcium carbonate associated with them in any significant degree. Then we have the tropics. And the tropics are the yellow bar. At the side there, you can see the blue, the green, the yellow, and the red. The tropical climate is where everybody goes to the Bahamas and enjoys the beautiful weather and such. That's typically tropical, and it ranges around 25, 30 degrees for reef growth. Then we look at evaporitization. And most humans don't want to be anywhere near that part of the curve. And it's can be as greater temperatures greater than 70 degrees centigrade. That's pretty doggone hot. The hottest I've ever been in is 50 degrees, so I can't imagine what 70 degrees really is. Humans have a narrow range of tolerance, and they expect things to be constant. Well, it's not going to be constant. They expect every year to be the same, but it's not. There's not a chance. Human environmental awareness, it's been growing since 1969 with the California oil spill. I was present at that spill, and we had to take this sign of our company, Shell, off the doors because people were coming looking for the company to do damage. And we dare not say we were geologists if we went to the bar, because there was a fight that was going to break out immediately. But even today, the environmental movement in that part of the world has changed its focus. It doesn't really deal so much with climate change as it does with local damage to the sailing community and to the local homes. So again, it's all about the rocks. When we look at rocks, there are things that we can see that tell us what is going on with the climate. And we can measure these things as well. So we have geochemistry, where we can look at isotopes, we can look at minerals, we can look at glacial structures if we're looking at glaciation. If we get into temperate zones, we've got fossil plants we can deal with, we've got vegetation, or invertebrates, and we've got a lot of coal that often shows up in the past. If we go into the tropical environments, we see lateritic soils. Those are the soils that turn red that you see in the tropics. And then there's other minerals: bauxite, gypsum, aragonite, calcite, dolomite, carbonate tidal flats and reefs. All of that stuff tells us we're in the tropics. And then we look at evaporites. We've got anhydrites, we've got halite, which is salt, we've got sylvites, we've got carnelites. And in that order, as the water evaporates, they come out progressively in that order. And those evaporites we can see in the subsurface as well. So what I'm going to do is take us on a stroll through time. And we're going to take you through the first order cycles of glacial climate. What you see up the side are glaciation, temperate zone, tropical, and evaporitization. And across the bottom, we have the age that we're looking at, starting with 600 million years. And we have the duration of each one of the geological periods. And so what I'm going to do is take us first and take a look at the glacial side, the glacial extreme. Then I'll go into the evaporate extreme. But these are the actual climatic conditions through geologic time. If we start with the first order cycle, if you look at the pre-Cambrian to Cambrian, it's 600 million years ago. You'll notice on the left, if you're looking at it from your side, looking at the left image, that's a paleogeographic map of the distribution of the continents on the Earth 600 million years ago, actually 545 million years ago. You'll notice the high concentration of land in the polar area, and that's below the 60 degree. And then when we look at 535 million years, you can see that the continents have moved away from the polar area and are starting to break up. And during that period of time, the climate was cool, it was warming up because we had improved global circulation. And so this accumulation of landmass at the poles, we would all understand as being a place where you'd expect to see glaciation. If we come to the Carboniferous, which is taking us somewhere around 290 million years, we had major landmass in the polar regions. Again, that's where the major glaciation was. So in that regard, the glaciations that we've encountered have all occurred when there was a large landmass at the pole. Today we have a landmass at the pole. It's Antarctica. In the Arctic, we're starting to see changes take place, and there is warming up, but we don't know yet whether there's a relationship to breaking up of the continents. Interestingly enough, 48 million years ago, the Arctic Ocean was all fresh water. And that helped set out the conditions because fresh water at the poles freezes. And so very few people are aware that it was fresh water, but it's been well documented. So let's look at the other extreme. Let's look at the evaporation. And that's going to be up there on top where the E is showing up. And what you notice there is it's very hot. If we look at Alberta, 400 and some odd million years ago, you look at Alberta, it was a salt basin. Thousands of feet of salt were deposited. It was evaporated out. The whole place was salt. Temperature here was greater than 50 degrees centigrade. And so this was something that resulted as the continents split up and then moved toward more tropical areas. At the same time, if we go through the Triassic, which is somewhere around 220 million years, this is a picture of Morocco up against Nova Scotia. And at that time, when it started to break apart, salt deposits were deposited in a narrow band of upwards to 100 kilometers wide and extended all the way down to the Gulf of Mexico and even into Brazil as the continent spread apart. So we had evaporitization going on at that time. It was very hot. There was no evidence of glaciation anywhere on the Earth at that point in time. But soon as Morocco started to move away from North America, we started having fresh water come into the system. And that fresh, what I mean by fresh, it's really marine water. And as that marine water came into the system, it warmed up the system, started to cool down the system from the evaporites. And by the time, at 180 million years, it was about the width of the Red Sea, as we see it today. And so, as the continents started to spread apart from evaporitization, things cooled down. And as you broke apart from glaciation, you warmed up. And this is well documented. So then let's look at second order cycles. These are superimposed on top of these first order cycles. So there's a few second orders that you can see up on the evaporite side. I haven't put in any second orders on the glaciation side because they're shorter of duration and there's not enough space to put them in. But we're going to choose some of them. For instance, the Silurian, which is about 400 million years. And this may not mean much to many of you, but the Michigan Basin had a sea level drop of 600 feet during the Silurian. Sea level drop because the water was evaporating. And and what you see are alterations between, you see the A1E, the A1C, the A2E, the A2C. E stands for evaporite, C stands for carbonate. The evaporite is the hottest time. The carbonate was cooled down, but it's still nice and warm. It was tropical. So these are second cycles, and there are at least 7 intervals in the last cycle, but there are 7 main cycles on top of that. And to give you just a quick sense, we can go into the rocks and tell an incredible amount about these. This is a northern Michigan reef where the sea level dropped 600 feet. So this thing was sticking up as a big rock pinnacle, surrounded by seawater of very highly saline character. And gradually the water rose, and the evaporites or the salts thickened up, which is the green. And then you can see that we have toward the top there, we have a high sea level, and we have this white cap that's draping over everything, and that has different water depths associated with it. And so we were able to identify completely what was going on just after the seawater started to come in and the salts formed. So we could recognize climate very, very easily in that situation. If we go through the Mississippian time, Mississippian was characterized by a whole series of sea level, seawater inundation and seawater removal from the region. And you'll notice that the Kansas Geological Survey attributed all of that to glacial sea level changes. It's well documented in the whole of North America. If we go to the end of the Permian, and what we have is called the Zechstein, which is in the Netherlands. The green represents salt, the purple represents anhydrite, the blue represents carbonate, and the yellow represents sandstones. But you can see the basic point of this is cyclicity, second order cycles of second order cycles of warming and cooling, but never going beyond the tropical. So, given those kinds of relationships, what about CO2? Is it a consequence of all of these continental drift issues, or is it a cause? This was work that was done in 2011, and what you're looking at up the side is the concentration of carbon dioxide. And we're talking about 290 million years ago. We've got time across the bottom. And you see the curve bouncing up and down, and you can see they've identified where the glaciations have occurred and where the non-glaciation. But the thing is quite intriguing. When there was glaciation, the carbon dioxide concentration was 200, but certainly less than 400. The only other time that has occurred in geologic time that we've finished recording is today. We are in a glaciation with we're in an interglacial, and it's the only time in geologic history, other than the Permian, that carbon dioxide was less than 400 parts. And yet, in between times, look at the carbon dioxide level, 3,600. It went up to 4,000 in some instances, and therefore 10 times what we see today, and the Earth is still here. And so those that want to focus on the damage that the carbon dioxide is going to carry out, we have to recognize that it's simply that the carbon dioxide is really a consequence of the climate occurring. When it's cold, carbon dioxide is very low. When it's hot, carbon dioxide is very high. And chemically that can be verified as a natural process. And so in this instance, we can see clearly that glaciation, it was down around 400. Today it's about 403. And in between times, in the warmer times, it was 10 times what we have present day today. The other glaciations at the end of, or the beginning of the Cambrian and at the end of the Ordovician, all that research is going on right now, but the results that are coming out are consistent with what we see for present day and for what we see in the Permian. The carbon dioxide under the glaciation drops to less than 400. If we look at the Pleistocene, this is our time. Up the side is concentration. Across the bottom is 650,000 years. And the green line really doesn't mean anything. It just helps you separate the warming above from the cooling below. But if you look at the concentration of carbon dioxide during the coolest times, it's less than 200 essentially. And in the warmest times, it goes up to almost 300, but today we're up over 400. Now there's a really interesting point here that the average length of an interglacial, which relates to the yellow portions, the average length of an interglacial is about 45,000 years. We are in an interglacial. We have been in this interglacial somewhere between 12,000 to 20,000 years. That means we've got somewhere between 25 and 30,000 years left to go if we're going to go back into another glaciation. And you notice after every interglacial, it goes into a glaciation. So we've got 25 to 30,000 years before we go back into another glaciation, if in fact that's what we're going to do. But if we are in fact at the end of glaciation at this point in time, and we are looking at a curve that is developing relative to the first order curve that we've been addressing, then we could go all the way up to an evaporitization just as a result of Earth processes. And so I'm certainly not going to be around 25,000 years from now to know what happened. I don't know of any way to predict what will happen, but it's certainly a really intriguing point. Are we at the end of an interglacial and going in and going on a first order? It could be. And if that's the case, we don't have a chance of stopping anything. Can't stop it anyway. Then there's lesser order cyclicities. And they're even a higher frequency than, and this was actually put together by Neil Hutton for the CSPG. And I like this because it shows a series of coolings in gray and warmings in yellow. And there's 7 of those cycles present in this picture. And well, most of the stories that we hear from the climatologists relate to the Little Ice Age and to present to today. So they're showing everything's warming up. They ignore everything that went on before. But this is all scientifically, geologically, archaeologically, biologically documented. So, what are the rocks telling us? We've got a bunch of cycles: glaciation to evaporitization, continental drift is first order, and it's on the order of hundreds of millions of years. We have second order, where the interglacials, we see the reefs and salts, we see the inter-evaporites, which people haven't studied, by the way, at this point in time, but they exist. They occur on tens of thousands of years. We have another cycle where we have glacier advances and retreats, and those are thousands of years. We have cooling and warming cycles, which might be a fourth order. That's your little ice ages and your little evaporite ages. Then we have others where we have seasons, which are annual, and we have cooling and warming cycles related to daily. In reality, what of these were caused by man? I don't know where on the chart you want to say man started causing the trouble, because the rocks are telling us this is just plain normal. So lessons. It's clear that climatic oscillations have occurred through geological time and their standard operating procedure. That's to be expected. The data show it, and it's well documented in the geologic knowledge literature. The rock data demonstrate detailed cyclicity, but new technologies are developing all the time, and so we're learning better how to read the language of the rocks. Where is the future going to lead us? We only live 70 years. We don't have the slightest idea what's going to take place. Lower temperature equals low CO2. Higher temperature or elevated temperature means higher CO2. And based on these data, I have to conclude that CO2 is a consequence, not a cause. Global warming is inevitable. Depends upon where we are on the interglacial or the first order or second order cycle. It really depends upon that. And if we're in a first order evaporitous oscillation, nothing's going to stop it. So we need to focus more on the reality concerns of human activities. For instance, population growth. In 1986, Earth's population was 5 billion people. Today, it's over 7 billion. In 2024, it's going to be 8 billion. In 2038, it's going to be 9 billion. In 2050, it's going to be 10 billion. Where are we going to put them? How are we going to feed them? They all want to live like we do. There's major concerns in that regard. Pollution. You add another 3 billion people to this earth, you've got a pollution problem. And I hate to mention this at dinner, but human excrement. Montreal felt free to dump it in the river. And they add 3 more billion people, and you know that you've got a serious problem. So we need to be addressing these issues, but they're politically very difficult to deal with. So climate will change regardless of what we do, and no politician will ever change what the earth has set for us. Thank you.